Scientists use large numbers like the weight of an elephant or the distance to the moon or even the speed of light. We can write these numbers that have so many zeros in a shorter way called scientific notation. Scientific notation is also called standard form. There are two parts to scientific notation. The first part is called the coefficient and is a number between 1 and 10. This is multiplied by the second part, which is the number 10 raised to an exponent. For example, an elephant has a weight or a mass of about 7,000 kilograms. Let's convert this number to scientific notation. 7,000 is 7 multiplied by 1,000, and 1,000 is 10 cubed, or 10 to the exponent of 3. Here's a quicker way. Write the decimal point in 7,000. The coefficient is the 7. Write the decimal point in 7. Now count how many places the decimal point was moved from 7,000 to 7. 3 places. So the exponent of the 10 is 3. Another example. The distance from the Earth to the Moon is about 400,000 kilometres. That's 4 multiplied by 100,000, and 100,000 is 10 to the exponent of 5. Let's do the quicker way. Write the decimal point in 400,000. The coefficient is the 4. Write the decimal point in 4. Now count how many places the decimal point was moved from 400,000 to 4. 5 places, so the exponent of the 10 is 5. The distance from our Earth to the Sun is about 150 trillion kilometres. This time the coefficient is 1.5 because the coefficient must be between 1 and 10. The decimal point was moved 11 places, so the exponent is 11. Here is the weight of the planet Mercury in kilograms. The coefficient is 3.301. The decimal point has moved 23 places. In scientific notation, this is 3.301 multiplied by 10 to the exponent of 23. The height of this astronaut is 1.8 metres. The coefficient is 1.8. In this example, the decimal point has not moved at all, so the exponent is 0. In scientific notation, this astronaut has a height of 1.8 multiplied by 10 to the exponent of 0. Scientists also use very small numbers, such as the size of bacteria. Here is the size of one bacterium. It's 5 millionths of a metre, or 5 multiplied by 1 millionth. To convert this very small number to scientific notation, we do the same as with large numbers, except that the exponent is written as a negative number, like this. It's 5 times 10 to the exponent of -6. A virus is even smaller. It's a very tiny 300 millionths of a metre, or 3 multiplied by 100 millionth. In scientific notation, that's 3 times 10 to the exponent of -8. Want to know how big an atom is? It's 1/10 trillionth of a metre. In scientific notation, an atom has a size of 1 multiplied by 10 to the exponent of -10 of a metre. Now let's convert scientific notation back to ordinary numbers. A robot sorts 5.08 multiplied by 10 to the exponent of 3 parts per day. What is this as an ordinary number? The exponent of +3 means it is a large number, so we move the decimal point to the right 3 places. That's 5,080 parts. In space, this space capsule travels at 1.6 multiplied by 10 to the exponent of 7 metres per second. How fast is this as an ordinary number? Well, the exponent of positive 7 means it is a large number, so we move the decimal point of 7 places to the right. That's 16 million metres per second. The eye of this ant has a width of 2 multiplied by 10 to the exponent of negative 3 metres. The exponent of negative 3 means that it is a small number, so we move the decimal point to the left 3 places. It's 0.002 of a metre wide. A red blood cell has a diameter of about 6.2 multiplied by 10 to the exponent of negative 6 metres. The exponent of negative 6 means that it's a small number, so the decimal point is moved to the left 6 places. The cell is 0.000062 of a metre wide. Are you ready for a challenge? In this example, we will learn to multiply using scientific notation. The mass of our Earth is 6 multiplied by 10 to the exponent of 24 kilograms. Astronomers have discovered 22,000 planets that are the size of planet Earth. What is the total mass of all these planets? The mass of the Earth is multiplied by the number of planets. Let's convert the number of planets to scientific notation. 22,000 is 2.2 multiplied by 10 to the exponent of 4. First we rearrange the numbers. We'll multiply the coefficients. 6 multiplied by 2.2 is 13.2. When multiplying numbers that have the same base, like 10, we add the exponents. So 24 plus 4 is 28. That's 10 to the exponent of 28. There's one more step. The first part, the coefficient, must be between 1 and 10. So we divide 13.2 by 10 to get 1.32, and then give that 10 to the second part, so the second part becomes 10 to the exponent of 29. Look at what the mass of all these planets is in ordinary numbers. Here is another challenge to multiply with scientific notation. Light travels at an incredible speed of 300 million metres per second. How far does light travel in 1 hour, which is 3,600 seconds? First, we convert both ordinary numbers to scientific notation. 300 million is 3 times 10 to the exponent of 8. 3,600 is 3.6 times 10 to the exponent of 3. We rearrange the numbers. 3 times 3.6 is 10.8. When multiplying numbers that have the same base like 10, we add the exponents. So 8 plus 3 is 11. That's 10 to the exponent of 11. There's one more step. The first part, the coefficient, must be between 1 and 10. So we will divide 10.8 by 10 to get 1.08, and then give that 10 to the second part, so the second part becomes 10 to the exponent of 12. In ordinary numbers, that is a very long way. Now here is a challenge to divide using scientific notation. The largest dinosaur was 30 metres tall. That's 3 times 10 to the exponent of 1. A man is 2 metres tall. That's 2 times 10 to the exponent of 0. How much taller is the dinosaur than the man? Well, a quick way is 30 divided by 2 to get the answer that the dinosaur is 15 times taller than the man. Let's do the same question by dividing using scientific notation. The answer is easier to do if we write the numbers like a fraction. 3 times 10 to the exponent of 1 is divided by 2 times 10 to the exponent of 0. 3 is divided by 2 to get 1.5. And 10 to the exponent of 1 is divided by 10 to the exponent of 0. Now when dividing numbers that have the same base like 10, we subtract or minus the exponents. So 1 minus 0 is 1. That's 10 to the exponent of 1. 1.5 multiplied by 10 to the exponent of 1 is the same answer of 15. Another bigger dividing challenge. Our Sun has a diameter of 1,400,000 kilometres. That is 1.4 times 10 to the exponent of 6. Our Earth has a diameter of only 13,000 kilometres. That's 1.3 times 10 to the exponent of 4. How many Earths can fit across the Sun? First, we'll use ordinary numbers to divide these. That's 1,400,000 divided by 13,000. That's approximately 108 Earths that can fit across the Sun. Now we'll do the same question and divide using scientific notation. We'll write the numbers like a fraction. 1.4 times 10 to the exponent of 6 divided by 1.3 times 10 to the exponent of 4. 1.4 divided by 1.3 is 1.08. Now 10 to the exponent of 6 is divided by 10 to the exponent of 4. When dividing numbers that have the same base like 10, we subtract the exponents. So 6 minus 4 is 2. That's 10 squared. 1.08 times 10 squared is about 108 Earths. That's the same answer. Here is the final dividing challenge. A bacterium is 5 multiplied by 10 to the exponent of -6 metres wide. A virus is only 4 multiplied by 10 to the exponent of -8 metres wide. How many viruses can fit across a bacterium? First, we'll divide these using ordinary numbers. That's 0.000005 divided by 0.0000004. That's approximately 125 viruses that can fit across a bacterium. Now we'll do the same question and divide using scientific notation. 5 times 10 to the exponent of -6 divided by 4 times 10 to the exponent of -8. 5 divided by 4 is 1.25. 10 to the exponent of -6 is divided by 10 to the exponent of -8. Subtract the exponents. -6 minus -8 is 2. That's 10 squared. And 1.25 times 10 squared is the same answer of 125 viruses.